Alrighty, folks, so let's move in now to kind of the second half, although it's not quite half, it's two lessons of the trigonometry unit. So here we're going to actually start looking at like solving equations that involve our trigonometric ratios, but all of those skills we talked about in the previous three lessons are not going anywhere. In fact, they're going to be one of the main tools we rely on in order to solve these trigonometric equations. So as always, here are, the big ideas, the key takeaways, the main skills we hope to be able to have by the end of this lesson, and practicing the lesson and meeting with me as needed to go over whatever concepts you're not quite sure about. But yeah, use that as a little checklist, and let's jump in. So let's start out with a little bit of review from Math 20 here, okay? And even just a review in general of, one of the most fundamental concepts in math. What does it actually mean to solve an equation? Well, it just means, again, you have some unknown value in your equation. Solving that equation means figuring out what that unknown value is, right? In other words, find the value of the variable that would make the equation true. In other words, make the left side equal the right side, right? I mean, to solve 2 plus x equals 7, what we're saying is 2 plus some mystery number equals 7. And we can figure out through some algebra or some just even thinking about it that x would need to be 5, right? That's what we've done. We've solved the equation because that's the value of x that would make this equation true. It would make the left side equal the right side, right? So that's what it means to solve an equation. So what we're doing when we're solving a trigonometric equation, typically anyway, most of the time, the unknown variable is an angle. We're trying to figure out an unknown angle that would solve an equation. So what we're going to make use of is all the stuff we've been talking about, those special triangles and the quadrantal angles. In other words, the unit circle, right? All of those special angles along the unit circle that, again, we don't have to have memorized. I don't even have it memorized. I'm a math teacher. I think about the special triangles and how they're oriented in quadrant 1, 2, 3, or 4, and that tells me all the information I need to know along with cast and just thinking about those ratios. Okay, so we can make use of those. We can make use of the coterminal angle stuff we know, and sometimes we can even use inverse trig ratios where those don't quite, where the special angles don't quite work out if we're dealing with something that might not be a special angle. Okay, but we'll use all of those skills in order to determine what the angle needs to be in order to solve the equation. So let's just do a quick recap of the trigonometric equations we solved in Math 20, what we did, what steps did we follow. Okay. So the first thing that we're going to do here is isolate the part of the equation that has the trigonometric ratio, right? You want sine x equals stuff, or tan x equals stuff, or even cosecant x equals stuff, right? That lets you start thinking about, okay, what angle might give me this ratio, right? So just to show you what I mean here, if you had, let's say, 2 sine x plus 1 equals 0, what we're trying to do is figure out what value of x, what angle could we take the sine of that would make this equation true. And it's a little tricky to think about in this form, right? Because we'd have to say, okay, well, we have to take the sine of that angle, then multiply it by 2, and then add 1, and we want that to equal 0, right? It's kind of hard to use our trig knowledge here to figure out what that means. But if we rearrange it, if we isolate the trig ratio, we would get, right, subtract 1 from both sides, divide both sides by 2, and we'd see that, aha, so sine of x, whatever x is just equal to negative 1 over 2. Whatever this angle is, its sine ratio needs to be negative 1 over 2 in order for it to make this equation true, to solve that equation. Okay, so once we know that, we can use our special angles, in other words, the unit circle, if it's one of the special angles, if it has a reference angle of 30, 60, 45, or 0, 90, 180, 270, 360, of course, radians, all of those as well, okay? If it's not one of our special angles, we'll need to use inverse trig ratios, but we've done that before. We'll see examples like that today again. Okay, to then find our reference angle. Remember, in this step, we don't want to include any negatives in our ratio. So for example, in this one, yes, we know that sine x is really -1/2, but we're just trying to get a reference angle, and then we'll use the stuff that we know to place it in the correct quadrant and figure out, what that angle would actually be, knowing that it's actually negative, okay? But when just getting the reference angle, for this one, for example, we would just be doing, if we had to use our calculator, which we wouldn't for this one because this is one of our special angles, but we would just say inverse sine of 1/2 to get the reference angle. Then we'd think about what the fact that it was really -1/2 means for the quadrant that it's in. So continuing the above example, a sine ratio of 1/2 implies a reference angle of 30 degrees, right? That's just using our special triangle. So I saw a 1, I saw a 2, I thought, okay, what reference angle would have, its sine? So we would have an opposite of 1, a hypotenuse of 2, right? What would this angle be? And we can recognize that, oh, this is one of our special triangles, right? Even if we didn't immediately recognize it, we could realize, well, what would this side be? Well, 2 squared minus 1 squared is 4 minus 1 is 3. Square root that, sure enough. This is our, 1, 2, 3 triangle, they sometimes call it, okay? This is our 30, 60, 90 triangle, okay? Like I've drawn off to the side here, okay? So now we know that it has, whatever our angle is, it must have a reference angle of 30 degrees because it has a sine ratio of 1/2. That's what 30 degrees has as its sine ratio. So this thing has a reference angle of 30 degrees. Now be careful, that doesn't necessarily mean x is 30 degrees, right? We know that there are, in just one rotation, there are 4 angles that have reference angles of 30, right? So now we'll just have to think about cast, okay, with our reference angle to determine the actual solution angles. What is x? Okay, so if the domain is from 0 to 360, that means there's going to be 2 solutions because each ratio is positive in 2 quadrants and negative in 2 quadrants, right? So sine of 30, like the absolute value of sine 30, is 1/2 in 4 quadrants, right? But then it's positive 1/2 in 2 quadrants, these two, and it's negative 1/2 in the other 2 quadrants. So for us in this example, we know that whatever x is, sine of x is negative 1/2. So it must be in quadrant 3 or quadrant 4 because cast, right? Sine is positive in the first quadrant where they're all positive, and in the second quadrant where only sine is positive. It's negative down here. So if sine of our mystery angle is negative 1/2, think about what we know now. We know it's got a reference angle of 30, and it must be in quadrant 3 and 4, okay? Just a side note here, we will see this today. You may also need to use your knowledge of coterminal angles if the domain is beyond 0 or 360, right? If it's something like from 0 to 720, you're going to have even more solutions because you can do 2 full rotations to find all the possible angles. Okay, so again, just working through this above example, we've kind of been doing that as we go, but the reference angle is 30, right? We established that here. Sine of 1/2 tells us the reference angle is 30. Now between 0 and 360, there's 4 angles that give that reference angle. We already talked about that. But our equation was not sine x equals 1/2, it was sine x equals negative 1/2. And sine is only negative in quadrants 3 and 4. Therefore, our solutions are, well, what's in quadrant 3 with a reference angle of 30 degrees? Because that would have a sine value of negative 1/2, right? Well, 210 is, right? Because it's 180 plus another 30, right? See how helpful a quick sketch is? And then what's in quadrant 4 with a reference angle of 30 degrees? It's 330, because again, not a full 360, we're stopping 30 degrees short of it. So 360 minus 330 tells us that our other angle is 330 degrees. So this equation has 2 solutions. 2 sine x plus 1 equals 0 has 2 solutions. X could equal 210 degrees and x could equal 330 degrees. Those are both valid solutions from 0 to 360, which we should check. Okay, it didn't specify that here. For this example, we'll just say for 0 to 360. I should probably add that into the notes. Okay, so let's try out some examples, some Math 20 type examples, except this one has a cosecant, but very similar to ones you would have seen in Math 20 to get back in the swing of it. All right, so the first one we've got is that root 2 times the cosine of x equals 1. And they're telling us we're just solving between 0 and 360. Okay, so we're expecting two solutions for this situation. Because again, cos x is going to equal something, either positive or negative, and cos is positive in two quadrants and negative in two quadrants. So step one, right, we need cos x equals stuff. This root 2 is making our lives a little tougher, right? Now we're thinking about, okay, what angle when I take the cos of it and multiply it by root 2 equals 1? That's a lot harder than just first. Let's isolate cos x, right? Isolate the ratio, okay? That's going to be pretty quick because all we have to do here, cos x is being multiplied by root 2, so let's divide both sides by root 2, since root 2 over root 2 is just 1. And now we've got cos x equals 1 over root 2. See what I mean? It's now a lot easier to think of just about, okay, what angle has a cosine ratio of 1 over root 2, as opposed to trying to think about what angle when I take cos of it and then multiply it by root 2, it equals 1, right? That's why we want to isolate our ratio first. And now, hey, do you have that a little alarm going off in your head? 1 root 2. Sounds like this might be one of our special ones. Let's see. Okay. So we're already kind of on to step 2 here. We're getting the reference angle. Maybe I'll make note of that. Step 2, reference angle. Okay, so we're asking ourselves, what reference angle would have a cosine ratio where, well, the adjacent is 1 and the hypotenuse is root 2, right? X is 1, R is root 2. So let's think about that. Adjacent 1, hypotenuse root 2. Okay, this is not our 30, 60, 90. This is the 45, 45, 90 triangle, right? 45. I'm working in degrees because they gave the domain in degrees, which, again, whatever they give us is what they want us to work in, okay? So this is that 1, 1, root 2. Two equal angles, two equal sides, and to make things nice and easy, we make the equal sides 1, because 1 is very nice to work with. So now we know, I mean, that's all of step 2. Our reference angle is 45 degrees, okay? But don't forget, that's just the reference angle. That's not necessarily the actual angle x, okay? So I might actually, instead of calling it theta, maybe I'll call it x reference because the symbol they're using to represent the angle here is x, not theta. Okay, so step 3 now, we've got to recognize that that's just our reference angle. There are, 4 angles that have reference angles of 45. So let's figure out first what quadrant we're in, or what quadrants we're in, I should say. Okay, well look, cos x equals positive 1 over root 2. So where is cos positive? Cos x is greater than 0, right? Well, that only happens in quadrants 4 and quadrant 1. Okay, so now we know we're looking for 2 angles as our solution, and they're going to be in quadrant 1 and quadrant 4. Okay, and that's step 3. I mean, to be honest, we don't always split these up into 4 steps, but I'm just kind of, and like label them as these separate 4 steps, but I do just want to remind you it really is always kind of this same process, right? Figure out what your ratio is, then use that to get a reference angle, then use the sine of it to figure out what quadrant you're in, and then use the relationship between the angle and the reference angle in those quadrants to find the angle itself. So find x. X is our angle here. Okay, so we're in quadrant, I'll do them separately here. Let's do quadrant 1. Quadrant 1's nice and easy because in quadrant 1, x just equals the reference angle, right? X just is the reference angle. When we're in quadrant 1, if we think about it, right, here's our angle x. Here is, that's the reference angle, 45. That's x. This is the reference angle. They're just the same angle. So if for quadrant 1, the solution we get is 45 degrees. Okay, always nice when quadrant 1 shows up. That one's super quick and easy. Not that the other ones are terribly difficult either, but quadrant 1, you just gotta, you already know the reference angle, so you know the angle too. Okay, now quadrant 4, we've got a reference angle of 45 degrees. We want to know what is the angle itself, right? Well, use those relationships, right? All the way around would be 360. We stopped 45 degrees short of 360. So x is going to be 360 minus 45 degrees. And therefore, our other solution for x is that it is 315 degrees. So two solutions, 45 and 315. And we can always verify by putting these, back into the equation we started with, doing cos 45 times root 2, does that equal 1, right? Could put it in your calculator, but you can actually also check that just using the ratios we know from our special angles, right? Cos of 45 we know is 1 over root 2. Sure enough, 1 over root 2 times root 2 is 1, right? We've verified that solution. 315 through a similar process. We'd have to think about it in 4 quadrants, but we could see it has a reference angle of 45. Cos will be positive, and then adjacent over hypotenuse. Cos of 315 is also positive 1 over root 2, and sure enough, it works out. All right, let's try this one here. Basically a Math 20 example, except that they've swapped out sine, cos, or tan for a cosecant, so that technically makes this a more Math 30-ish one. Let's give it a shot. Oh, and radians. That also makes it Math 30-ish. So first up, right, let's isolate that trig ratio so that we can think about what angle might have that ratio, right? So we'll isolate ratio. In this case, it's cosecant x. So I'm going to do add 6 to both sides, right? Because right now that's being subtracted from 3 cosecant x. And then divide both sides by 3, because cosecant x is being multiplied by 3. And that'll give us that cosecant of x equals 2. Which is perfectly fine to work with. There's nothing wrong with that. But if you want, we can also switch that. If cosecant of x is 2, remember cosecant is 1 over sine x, right? It's the reciprocal function of sine x. So then sine x is just 1 over 2. And there we go. Now we understand that we're just looking, okay, for an angle whose reference angle, the sine function, or the sine operation on that angle would give us 1 over 2. Well, that sounds like a special triangle, maybe, right? 1s, 2s, root 3s, root 2s. Those are kind of the things that we're on the lookout for to be able to use our special angles. So thinking about this, what angle, if this is our reference angle, would have an opposite of 1 and a hypotenuse of 2? Oh, this is our, do you know what goes here? This is the 1, 2, root 3, right? Opposite is 1, hypotenuse is 2. So what angle is this if it's next to our root 3? Yeah, you might have said 30 degrees, which is true, but they gave us this in radians, right? So it's 30 degrees, sure. But let's work in radians since they gave us radians, and we are starting to know that radians aren't so scary, right? They're actually a really good way to think about angles. So our reference angle is pi over 6, one of our special reference angles that is associated with the special angles around the unit circle. So now let's figure out what quadrant we could be in. Because once we do that, we're basically there. We know the reference angle, we know what quadrant we're in, we can figure out any angle then that we need to. So what quadrant are we in if, help me out, if sine x is positive 1/2? There's 2 places where sine x could be positive 1/2. You got it, quadrant 1 or quadrant 2, right? Because sine x is only greater than 0 in quadrant 1 and 2. So quadrant 1 and quadrant 2. All right, so now, right, that's all the information we needed to know to figure out what an angle is. If you know its reference angle and the quadrant it's in, you can use those relationships to figure out the angle itself. So quadrant 1, hey, always nice when it's quadrant 1, right? Because we just know that in quadrant 1, the reference angle is the same as the angle, since it's always referenced to the positive x-axis. So in quadrant 1, our angle, our mystery angle x, is just the same as our reference angle, which we've established is pi over 6. So there we go. That is one possible valid solution. Okay. The other one is going to happen, as we've established, in quadrant 2. So let's think about quadrant 2. What angle is in quadrant 2 that has a reference angle of pi over 6 or 30 degrees, right? Again, we'll think about it, okay? All the way to pi would be, a 180. All the way to pi, we didn't quite make it there. We're pi over 6 short of pi to make that angle, okay? So let's think about how we could figure it out. Well, we could take a full pi, 6 over 6 pi, and subtract the 1 pi over 6 that we didn't quite do, right? That reference angle there tells us that we're pi over 6 short of a full pi for this angle. So that means our x is, again, get a common denominator if you like, right? Pi, multiply it by 6 over 6 to express it as a fraction over 6. 6 pi over 6 minus 1 pi over 6 gives us that. The other solution is x equals 5/6 of pi, right? So those are our two solutions. X equals pi over 6 and x equals 5 pi over 6. All right, and again, we could always check our work. Take that pi over 6, put it in for x here, work that out and see if it's true. See if left side really does equal right side. Because if so, that's all we found then. We found the solutions to that equation. Okay, let's really move into some Math 30 stuff here that we definitely did not see at all in Math 20, but it's really fun. And so that new thing that's definitely new to Math 30 is that we're going to see what we call second-degree trigonometric equations, which means what you think it means from our polynomial unit, right? Means we might see situations where ratios are raised to some power, okay? So we're now also going to see situations where we have quadratic degree 2 trigonometric equations, right? Meaning that the trigonometric ratios might appear in more than one term with exponents of 1 and 2. So instead of just having situations like this, where it's, okay, get cos x by itself or get cosecant x by itself, right? Now, we can't really just get something that's like tan theta equals stuff, right? Because we've got a tan squared theta and we've got a tan theta, okay? So we can't just, bring all the tan, like it's not a situation where we can just have tan theta equals stuff. We've got a tan squared and a 10, right? Tan, right? Just like in Math 20, where you had x squared plus 5x equals 6. There's nothing you can do to just get x by itself anymore because there's two terms where x appears and it has a different power in each. But guess what? You know how to solve this. You also know how to solve this, okay? It's actually the exact same process with some trig stuff tacked on at the end. So basically, we're going to use Math 20 skills to get it to a situation where then we can take over and do our trig stuff that we did in Math 20. Okay, it's really just building on the ideas we've seen before. So the overall process is exactly the same, but as we've discussed, we'll have to rethink that step 1 a bit. We can't simply isolate tan x. Instead, does this sound familiar? We're going to have to bring all terms to one side and then factor or use the quadratic formula, right? That's exactly what we always do with a quadratic equation. Nothing changes here because our quadratic equation now involves a trig ratio. It's still the same idea. It's exactly like when you went from solving linear equations in Math 10, where you could just isolate x, right? Like these, where we could just isolate cos x or isolate cosecant x. And then we got into Math 20 and we couldn't just isolate x anymore. Well, same idea now, but with trig, right? We can no longer just isolate the ratio, but we can still bring everything to one side and factor it, like we would do to solve any quadratic equation, okay? So if we bring all terms to one side for this one, it gives us tan squared theta equals, this is what we started with. If I bring all terms to one side, I subtract 5 tan theta, I add 6, so that I have tan squared theta minus 5 tan theta plus 6 equals 0, right? Now, do you notice how this is the same as x squared minus 5 x plus 6, if instead of x, I say we have tan, right? Right, just quickly wrote this down to emphasize it a bit, right? Tan squared theta minus 5 tan theta plus 6 equals 0. This is just a quadratic equation, right? Tan theta is just a number, right? It is. It's just some ratio. What did x stand in for? Just some number that we didn't know yet, right? So this is the exact same process and thought behind it as this one, right? Yes, we're going to have to do some triggy stuff down the road, but it doesn't change the fact that, hey, this is a quadratic equation. It's just that we've got a tan x in place of just x, right? And so the same thought process, is the same things are going to apply. Okay, we'll get back to that in a second. Just two things I quickly want to talk about. The first is pretty straightforward, pretty quick. Be careful when we're writing these equations. I know it seems a little bit weird at first that this means, so tan squared x just means we're taking tan x and we're squaring it, okay? Why do we put the squared there? I know that seems kind of odd. Well, the reason is if I write this, what does that look like? It looks like I'm taking the tan of x squared, doesn't it? But that's not what we want to do. We want to take tan of x and square it. So we want to square tan x, not take tan of x squared. So I just wanted to quickly mention that, okay? That's where our squared goes when a tan is getting squared or any ratio is getting squared. The other thing I want to mention here before we move any further, okay, is that we need to be very careful here. It wouldn't have applied to this one, but it can come up. We'll see it in examples today. So I'm going to bring it up right at the beginning. Just like when you worked with quadratic equations in Math 20, you cannot use algebra to cancel out the ratios completely here, right? Otherwise, what can happen is that you can lose solutions. So just for an example, so you can see what I mean, I'll first do like a Math 20 example, right? Let's say that we had something like, x squared equals x, just to make it nice and simple. It might be really tempting to divide both sides by x, right? Because then our equation would become x equals 1. And you could say, oh, I did it. I solved for x. And you're totally right. X equals 1 is a solution to this equation. However, there's another solution, and we just lost it by doing that. By canceling out that x completely, there's a solution that's gone now that we could have gotten if we had followed the proper process for solving a quadratic equation, which is to bring everything to one side and then factor. So let's do that here and see if there's another solution we missed. I'm going to subtract x from both sides, so that x squared minus x now equals 0. Again, the reason we want to bring everything to one side is that when it equals 0, that makes it really easy to solve after we've factored, because we know we have factors being multiplied together, and the answer is 0, which is only possible if the factors themselves are 0. So now look, I notice that I can pull out a common factor of x, right? So x squared divided by x is x, negative x divided by x is negative 1. And that equals 0. Aha, look at this. There were actually two solutions. X could equal 0, right? If x equals 0, then I have 0 times whatever, doesn't matter. 0 times negative 1, which is 0. So x equals 0 is a solution to this equation, right? And so is the one we found the other way. X equals 1 is still there, okay? But we got both of them, okay? Now, this is a pretty simple example, but sometimes it might not be as obvious. We got to be careful. I know how tempting it is to divide both sides by x here, and it will give you a solution, but it will also lose a solution, right? Do you see that? Okay, so just be careful about that. Sure enough, they are both solutions. 0 squared does equal 0. 1 squared does equal 1. So just be careful about that, okay? To give a trig example, it's actually basically the same example. If you have cos squared x equals cos x, for example, it might be very tempting to divide both sides by cos x and get that cos x equals 1. And then there you go. You know that x is 0 degrees because cos of 0 is 1, right? But this equation here now actually has fewer solutions than we started with, right? We actually need to, if we bring everything to one side and factor, we'll be able to find all solutions, okay? So instead of dividing both sides by cos x and canceling those cos x's out completely and losing those solutions, we're going to bring it all to one side. Cos squared x minus cos x equals 0. Well, that we can now factor. We can pull cos x out as a common factor, right? Leaving us with cos x times cos x minus 1, right? Cos squared x divided by cos x is just cos x, and then negative cos x divided by cos x is just negative 1. This now gives us two conditions for solutions, right? When we divided both sides by cos x, we just got cos x equals 1. Now we can see that, oh, cos x could equal 1, sure, but it could also equal 0. Right? And then we would do our normal trigonometry stuff to figure out that, okay, well, if cos x equals 0, x could be 90 or 270. Cos x equaling 1, x could be 0, right? I'm assuming from 0 to 360, okay? Both of these do lead to solutions. In fact, this leads to two solutions. X could be 90 or 270, right? Or pi over 2 or 3 pi over 2. So by doing that there, we lost two solutions that we never would have known about it, okay? So that's why we need to be careful when doing these. We don't want to cancel something out completely on both sides. Whenever we're dealing with a quadratic equation, like you've always done, but including now when they're trigonometric, we want to bring everything to one side, then factor to solve. Okay, so let's get back to this example. We kind of took a little sidetrack there to remind ourselves of some important stuff, okay? But we've got here, right, again, ooh, I'm just going to rewrite that. That's a little messy. There we go. Okay. Notice how what we ended up with, tan squared theta minus 5 tan theta plus 6 equals 0. Whoops, I replaced my... There we go. Sorry, just quickly wanted to fix that. I noticed I switched it from how it was in the notes to an x. Let's say tan squared theta so that we're consistent with what this said, okay? Again, these are really, it's the same thing in terms of the type of equation we need to solve, right? Yes, we'll need to do more with the tan theta part once we figure that out, but in terms of just solving a quadratic equation, our first steps would be the same thing here, right? Getting back to our example, tan squared theta minus 5 tan theta plus 6 is really kind of the same as x squared minus 5x plus 6 equals 0, except that instead of x, we have tan theta. Which means we can do the same thing, bring everything to one side and factor. After all, x just stood in for some number, right? X was some unknown number. Tan theta is also a number. It's a ratio, right? Maybe it's 1 over root 2, or maybe it's root 3 over 2. Who knows? But we'll figure that out as we go later, okay? But it is just a number. So let's factor this the same way we would factor x squared minus 5x plus 6. So here we go. If I've got tan squared theta minus 5 tan theta plus 6 equals 0, right? Again, sometimes students like to, just to help them in their brain a little bit at first, replace the tan with an x and see if they can think about it. But what would you think about if solving this one? You'd ask yourself what multiplies to 6 and adds to this x coefficient here, right? Well, it's the same thing. What multiplies to 6 adds to this tan theta coefficient here. So we need two numbers that multiply to 6 and add to negative 5. We can think about that for a sec. Multiply to 6, add to negative 5. Hey, how about negative 2 and negative 3? That'd work, right? Negative 2 and negative 3. Right? So we could rewrite this just as we would then take this and rewrite it as x minus 2 times x minus 3, right? We can rewrite this as tan theta minus 2 times tan theta minus 3, right? If you go through and replace all those tan thetas with x's, do you see how this is nothing different than solving any other quadratic equation so far, right? It's just a tan theta is our unknown thing right now instead of an x. Okay, now think about how powerful that is. Because what would we do next in solving a quadratic equation? Well, we'd say, I'm multiplying these two things together, and the result is 0. That's only possible when this is 0 or when that is 0, right? When our two factors are 0. And so we can now use this, right? We can use this to say that, all right, so this equation could be true when tan theta equals 2, right? Tan theta minus 2 equals 0, so tan theta equals 2. Or when tan theta minus 3 equals 0, so when tan theta equals 3. And that just gives us, look what we've got. What was step 1 before? Isolate, get an equation and isolate for the trig ratio. Well, that's what we've done. We have 2 of them now to solve. So we might get up to now 4 solutions, and that's just if we're from 0 to 360. But it's really not anything different. It's just more of what we've been doing. Okay, it's the same process we would now follow from step 2 onward. We just have to do it twice, right, for each equation, for when tan theta is 2 and for when tan theta is 3. Okay, so here we go. From here, the steps are the exact same as the examples you were doing previously. Find the reference angles, then use cast to determine the solution angles themselves. We'll have more solutions because there's now 2 ratios to think about when finding reference angles, right? Tan theta is 2 and tan theta is 3. So let's go ahead and finish solving this one, right? Step 1, we kind of already did it up there. We figured out that tan theta could equal 2 and tan theta could equal 3. You know what? I'm just going to do tan theta equals 2, then we'll do tan theta equals 3, just to kind of keep things separate. So we'll do tan theta equals 2 here. We'll leave ourselves some room. Hopefully that's enough. And then over here, we'll do tan theta equals 3. All right, let's jump in. So if tan theta is 2, okay, let's now jump right into step 2 and get our reference angle, right? We want to know what angle would have a what angle's reference angle would give us a tan ratio of 2, right? I mean, we can draw it out to check if it's a special one. I don't think it actually is, though, is it? Right? Is there one of our special triangles, does it have opposite to adjacent 1? Because tan is opposite over adjacent, right? We do have ones that have 1s and 2s. There's the 30, 60, 90, but the 2 is the hypotenuse in that triangle, right? In the 45, 45 triangle, we've got 1 on these sides and then a root 2 as the hypotenuse. So this is not a special one. Not special, which is okay, because we can do what, we would typically do. We can say, all right, we know that tan of whatever this reference angle is supposed to equal 2 to solve this equation, right? Well, right now, tan is an operation. We're taking the tan of theta r. So how do we undo tanning, right? What's the inverse operation of tan? It's got a very creative name. It's inverse tan, right? Second function tan on your calculator, or shift tan on some calculators. So theta r must just be the inverse tan of 2. And if you put that in, always keep a few extra decimal places here. Don't overround, okay? I got 63.43 degrees. That's our reference angle for when tan theta equals 2. So any angle that has a reference angle of 63.43 will have a tan ratio equivalent to 2 or negative 2. Depending on which quadrants we're in, which leads us to our next step. Let's figure out what quadrants we are in. Okay, so here we go. Tan theta is 2, positive 2. So tan theta is greater than 0, right? Meaning that we are in quadrant 1 or 3. Those are the 2 places where tan would be positive. And we're looking for where tan is positive 2 specifically, okay? So step 4, right, if you like, step 4, we're now going to actually find the angles theta, okay? So 2 solutions we're expecting to find here just from tan theta equals 2. Then we're probably thinking we're going to find 2 more when we solve tan theta equals 3. So here we go. Let's figure out our angles. We want them to have reference angles of 63.43 degrees, and we want them to be in quadrant 1 and in quadrant 3. Let's do quadrant 1 first. That one's always nice and quick and easy, right? If this reference angle here is 63.43 degrees, well, that just is our angle, theta. So theta is 63.43 degrees. It said round to the nearest degree, so we'll say 63 degrees. One down, I'm predicting 3 to go, right? 2 for this equation, tan theta equals 2, and 2 more for this equation, tan theta equals positive 3. Okay, so in quadrant 3 now, we know that this has to have a reference angle of 63.43 degrees, okay? We're looking for what angle terminates in the third quadrant and has a reference angle of 63.43, right? A quick sketch helps us see here that, oh, it's just going to be, right, 180 plus another 63.43. We've gone past 180 by 63.43 degrees. So this theta will be 180 plus 63.43 degrees, giving us that angle is going to be 243.43 degrees, or to the nearest degree like it asked for, 243 degrees. We'll list all our answers neatly at the end, but I'm just putting boxes around them as we go so I don't lose them. Okay, there we go. Now, those would be solutions to this equation, right? Because they would make this factor equal 0, right? And we know they are solutions then, right? Tan of 63 is 2. 2 minus 2 is 0. Sure enough, if this is 0, left side equals right side, right? Tan of 243 is also 2. 2 minus 2 is 0, so 243 is a value of theta that solves this equation, makes it true. But there's a whole nother way we can solve this equation if tan theta equals 3. So that's what we're going to set out to do now, right? There we go. We know tan theta equals 3. We can think about, is this a special angle? I mean, is it, right? Is there any of our specials have opposite 1, adjacent 3? We have one where opposite is 1 and adjacent. Oops, sorry, I did that backwards. That should be 3 and 1, right? Opposite is 3, adjacent is 1, so that opposite over adjacent is just 3 over 1, or 3, okay? We have one where there's a 1 and a root 3, but not a 1 and a 3, so this is not special either. That's okay. We can just use inverse tan again, okay? So let's just use inverse tan to get our reference angle, theta r. Tan of this reference angle, and I know we don't have a negative here, but just a reminder, if this was equal to -3, we wouldn't include that. We would just use the 3 and then use cast to think about what that negative actually tells us about the angle within the 4 quadrants. So tan of our reference angle has to come out to equal 3, meaning our reference angle itself, inverse tan of both sides, gives us inverse tan of 3, and therefore our reference angle is, I got 71.57 degrees. Okay, so there we go. Now what do we know? We know we're looking for an angle or angles that have reference angles of 71.57 degrees. Otherwise, the tan of this angle couldn't equal 3. Next up, figure out what angles have a reference angle of 71.57 degrees. So let's get our quadrants. Okay, well, tan theta equals positive 3. So we're looking for where tan is positive once again. Well, where does that happen? It happens in quadrant 1 and it happens in quadrant 3. So very similar to our other one. Okay, now we're ready. We're looking for the angle in quadrant 1 that has a reference angle of 71.57 degrees. And we're looking for the angle in quadrant 3 that has that same reference angle. So what angle in quadrant 1, whoops, I forgot to actually say here, quadrant 1 and quadrant 3. There we go. What's this angle? If this is 71.57, yeah, theta is also 71.57. You got it. So theta is 71.57 degrees for quadrant 1. Okay, now we got to do quadrant 3, because that was another place where tan theta could equal positive 3. Well, I mean, same steps, right? We're in quadrant 3. We know we've got a reference angle of 71.57. So what is this angle itself, right? Well, it's going to be 180, but we're going past 180. How far? Yeah, 71.57 degrees past 180, giving us that this value of theta would be 251.57 degrees. Whoops, I didn't round this one to the nearest degree. It's okay, I'm about to report all of my angles as my final answer, so here we go. Now, before I do, I should probably check the domain. Okay, 0 to 360, right? Really, I should have checked that at the beginning, okay, because that could change where we were even looking in the first place. Sometimes it might say 0 to 180, meaning that you can just ignore quadrants 3 and 4, okay? But in this case, we just want 0 to 360, but not beyond 360 and not less than 0. So those really are all my solutions, right? I've gone from 0 to 360 all the way around, and that's all I actually wanted to include. I don't want to include, another full rotation, like 63 plus 63 plus another 360. That will be a solution, but it won't be a solution within this domain, right? We were limiting theta to just one rotation. We call these the principal solutions again, right? The ones that are within one rotation from 0 to 360. So summing it up, we've got that theta could equal, to the nearest degree, it could be 63 degrees. We found that it could be 72 degrees. We found that it could be 243 degrees. And we found that it could be 252 degrees. All of those are solutions to this equation. All of them would make it true, right? These two make this factor equal 0, and therefore they satisfy the equation. These two made this factor equal 0, and therefore they satisfy that equation. So do you see what I mean? Do you see how this is kind of putting our two loves together? It's putting factoring and solving quadratic equations on top of solving trigonometric equations, kind of, right? We factor to get these two solvable trigonometric equations, and then we do our usual trig stuff to actually find the angles that are the solutions. Isn't that cool? Fun, right? All right, let's do one here from a release diploma. It's a written response. Okay, this was worth 3 marks on the diploma. Keyword here, algebraically. What does that mean? Can you just punch it in your calculator and see what happens and write down the answer? No, that will get you 0 out of 3 marks, even if you have the right answer. Okay, algebraically means showing your math steps, showing your reasoning, showing your equation manipulation, all that good stuff, right? No numbers should just appear out of nowhere. We should show algebraically how we figured those out, okay? When in doubt, show more work, not less. Now, that depends on student to student, how much you think is an appropriate amount of work, okay? But someone who understands Math 30 should be able to read it and know that at every step you knew what you were doing and why you were doing it, okay? The other key thing I want to note here, state the solution as exact values. So put the calculator away as soon as you see that. Exact values, okay? What that means is no rounding, no irrational numbers just given to a certain amount of decimal, right? For example, root 3 over 2, that's an exact value, right? It's not rounded. It really is root 3 over 2, okay? Do you know what your calculator is going to say if you plug that in? It's going to say 0.866 and then a bunch of stuff. But root 3 is an irrational number. It never ends. And so you're going to have to round that eventually. Okay, it is not an exact value. Now, again, same thing happens if you were to say sine of 60, right? If you were to take 60 degrees and do sine of 60. On your calculator, what's it going to say? And I'm going to use squiggly equals here because it's not actually equals, it's approximately equal to, not exactly equal to, right? If you use your calculator, it's going to say sine 60 is equal to 0.866 and then some other numbers. That is a rounded value. It's not exact, right? We know from our special angles and our special triangles, the exact value of sine 60 is root 3 over 2. That's exact. That's not rounded. That really is what sine of 60 equals. So exact value, okay, it's something we talk about. It is not 0.866 for this example here, okay? So if you're putting stuff like sine 60 into your calculator or sine 30 or cos 45 and you're hoping to get an exact value out, you are not going to, okay? It's these ratios from our special angles that will allow us to write exact values. So as soon as you see exact values, put the calculator away and start thinking in terms of those special angles, which we always should be anyway, because honestly, they're quicker, easier, and lead to deeper understanding than just putting it in our calculator anyway. So with those couple warnings out of the way, let's try and algebraically solve this equation here. Here we go. All right, so the equation we're looking at here is secant squared theta plus secant theta equals 2, right? So we can see we're dealing with a situation where we've got a quadratic in terms of some trigonometric ratio, right? Secant is being squared here and has a power of 1 here. So we're not just going to be able to isolate secant. We're going to have to solve it as a quadratic, bring everything to one side, factor, all that fun stuff before we start even worrying about all the trig stuff. So let's go ahead and do that. Let's start here. So secant squared theta plus secant theta equals 2. As always, when we're solving a quadratic, right, our life gets way easier if we bring everything to one side. So I'm going to subtract 2 from both sides, because what that allows me to do is now once I factor this, I just need to figure out how to make either of the factors equal 0. Right? Which is a lot easier to do than think about factoring here and how to make them equal 2, right? Because that just means the factors need to be 0 if when I multiply them together, the answer is 0. So now we factor this, and again, right, do you see how this is really the same thing as x squared plus x minus 2 equals 0 if we replaced x with secant theta? Right? Since x just stands in for an unknown number, secant theta is a number, it's just some ratio we don't know yet, right? We can factor it and solve the exact same way. So we need to ask ourselves what two numbers would multiply to -2 and would add to +1. So multiply to -2, add to +1. Well, how about 2 and -1? Right? Those would do it. 2 times -1 is -2. 2 plus -1 is 1. So that means our two factors are secant theta plus 2. There's one factor. And the other is secant theta minus 1. And that equals 0, right? Rewrite it in its factored form. And again, this is why we brought everything to one side, because now I'm multiplying this by this, and the answer is 0. We're trying to figure out what value of theta could make this equation true. Well, whatever that value of theta is, it either makes this 0 or this 0 in order for their product to equal 0. Okay, and so this gives us our two equations that we're now going to go ahead and solve, right? Our two equations are, we need secant theta plus 2 to equal 0, and therefore secant theta to equal -2, right? And we need the secant of theta minus 1 to equal 0, and therefore the secant of theta to equal +1. And now we've got those two trig equations, and we're back in, back in the stage where we've got our trig ratio. We can figure out what its reference angle is, figure out what quadrants it could lie in, and therefore what the actual angle itself is. We just have to do it twice because we have two solution conditions, right? We need the theta that makes secant, the thetas, I should say, that can make secant theta equal -2, and the thetas that can make secant of theta equal 1. Okay, so that now becomes our goal. Let's go ahead and get our reference angles then for those two equations. So I'm going to say step 2, we're going to get our reference angles. Okay, so let's start out with the equation on the left. We need secant theta to equal -2. Personally, for me, I find it a little easier to think about by turning that secant into its cos equivalent, right? Secant is just the reciprocal of cos. So if secant theta is -2, which you could think of as -2 over 1, right? cosine is 1 over that. Cosine is 1 over secant theta. So then cosine of theta must equal negative 1 over 2. Now, that tells us that whatever our reference angle is, it needs to have a cosine ratio of 1 over 2, right? Again, we're going to ignore that negative while thinking about the reference angle because we're just trying to think, okay, what kind of triangle could this be part of? When it comes time to think about it within the 4 quadrants, that's when we'll consider what the negative tells us about the quadrant it could be in. So, is there a special angle or a special triangle we can think of that would have adjacent 1, hypotenuse 2? Well, hypotenuse 2, yeah, right? And adjacent 1, this is our 30, 60, 90. Or, since we're working in radians here, we're going to be thinking of not 30 degrees and 60 degrees, but instead pi over 3 and pi over 6. Okay, so 60 is pi over 3, right? It's 1/3 of 180. So 1/3 of pi. Okay, so there we go. Our reference angle for this one is pi over 3. We'll come back to that in a second, but let's first get our reference angle for the other solution condition, which is that secant theta could equal 1. So we need secant theta to equal 1. Well, that just means we need cosine of theta to equal 1 over 1, right? Which is also 1. So where does cosine of theta equal 1? What's the angle there? Do you remember? Well, right, we don't have to remember, we can think about it, okay? Cosine is adjacent over hypotenuse, x over r. So if adjacent over hypotenuse or x over r is equivalent to 1, that just means x is the same as r, right? Or adjacent is the same as hypotenuse. So that happens at an angle of 0 radians, 0 degrees, whatever you want to call it. Okay, we'll work in radians since this question is in radians. But that means this, right? If we pick a point on the terminal arm of that angle, right? Let's use the unit circle because that makes things easy. 1, 0, right? Well, r is 1 on the unit circle. X is 1 here, so 1 over 1, 1. So our reference angle here is actually just 0 radians. Okay, now it's time to talk about our quadrants, or to think about our quadrants. However, there's something there that I maybe should have pointed out at the very beginning, okay? But now we're at the stage where we'll have to think about it, okay? 2 pi is less than or equal to theta, which is less than or equal to 3 pi, okay? So be careful. It's not always just going to be from 0 to 2 pi, right? Here, our domain is limited. Let's think about that. We know that 2 pi is less than or equal to theta, which is less than or equal to 3 pi. So what is that? What does that look like? Well, again, we know this is 0, pi over 2, pi, 3 pi over 2, and then 2 pi, yeah, but we could keep going, right? If we did another pi, rotations, we'd be back to over here. That's 3 pi, right? So think about this, where our domain here is actually beyond 1 rotation entirely. That would be 2 pi right there. But we need to keep going past 2 pi to 3 pi. So it's telling us that's our domain, right? The smallest possible value of theta we can accept as a solution is 2 pi. The biggest is 3 pi. So whatever our solutions are, they're actually beyond 2 pi, okay? But that's all right. We're still going to solve it like we normally would, and then we'll recognize that, okay, but we might need to add 1 full rotation to this, okay? So that's our starting point. We know, we can kind of see we're just looking in quadrants quadrant 1 and 2, right? That's where we're limited to. 2 pi to 3 pi, that just falls within quadrant 1 and 2. After a full rotation, yes, but still in quadrant 1 and 2. Okay, so with that in mind, let's now think about our actual cast stuff. Okay, so for cos equals, or secant equals -2, or cos equals -1/2, same thing, okay? Cos is negative, and that happens in quadrants 2 and quadrants 3. But one of those we now know we're not interested in as a solution. Which one? Right, we don't want quadrant 3 because we're limiting our domain from 2 pi to 3 pi. This would be beyond 3 pi, right? So that's no good. So just quadrant 2, that gives us just one solution to find there. And then for our other equation, what was it again? Oh, right, just cos theta equals 1. Well, this is actually going to let us find our angle pretty quickly. We can do that right off the bat because, yes, cos theta equals positive 1, right? Cos theta equals positive 1. So we're looking in quadrant 1 or 4. However, we know that we're not including quadrant 4 because we're between 2 pi and 3 pi. We can honestly, at this stage, we know what our angle is going to be. It's 2 pi, right? We've established that the reference angle is 0. Kind of weird to even call that a reference angle, but it is. Like it's where we kind of could compare to, right? But it's also 2 pi. In fact, 2 pi is the lower limit of this, right? It can't be 4 pi. We can't go all the way around. So within this domain, the only place where cos of theta would equal 1 is at 2 pi, okay? So I'll save that for when we state our answers in the next step, but we've established that cosine of theta needs to be 1, and since theta needs to be between 2 pi and 3 pi, one valid solution must be theta equals 2 pi, okay? So let's now finally get our angles. We're going to get 1 we're expecting from this equation. So from secant theta equals negative 2, okay, we know that. What do we know about this equation? Remember, we learned that the reference angle needs to be pi over 3, and from this we learned that it needs to be in quadrant 1 or 2, and from cast we know that it needs to be in quadrant 2. Right? For cos to be negative and us to be between 0 and 2 pi and 3 pi, we need to be in quadrant 2. So we're looking for something that's in quadrant 2 with a reference angle of pi over 3. Now be careful, we're not actually looking for this angle, right? That's not between 2 pi and 3 pi. That's much less than 2 pi. So we need to go all the way around to 2 pi, and then that far, right? And then that far, okay? So how I might go at this is I would probably just figure it out within one rotation. So what I mean is I would maybe figure out just this part, right? And then I could worry about adding. How much do I have to add to that to get the actual angle theta? Another 2 pi. Right? It's just coterminal to what I've drawn in purple there. Orange is just coterminal to it, right? Purple is just another full rotation added onto that. So that's kind of my strategy here. I might say that our theta here, theta is going to equal 2 pi, right? A full rotation plus just this purple part here. And that purple part there would be, well, here's pi, right? Pi minus pi over 3. Okay, giving us that theta is 2 pi plus, well, pi minus pi over 3, that's 3 over 3 pi minus pi over 3, right? So 3 pi over 3 minus pi over 3, giving us that theta is 2 pi plus 3 minus 1 pi over 3 is going to give us 2 pi over 3. And we can think of 2 pi as 6/3 pi if we like, giving us 6 plus 2 is 8 pi over 3. So there's one valid solution, okay? From secant theta equals negative 2. Now, again, normally we would then say, okay, but where's the other place where secant theta could be negative 2, right? We know it's in quadrant 3. That could happen, but we're excluding quadrant 3 because of the domain, right? We're only looking between 2 pi and 3 pi. Quadrant 3 would mean we were beyond 3 pi, okay? So that's our one solution that we actually get from secant theta equaling negative 2. From secant theta equals 1, we already kind of talked about it, right? From secant theta equals 1, we know that we need to essentially have this situation where this is the terminal arm of our angle, because that's how we get cosine theta to equal 1. So what's our angle if we have to be between 2 pi and 3 pi? It must just be 2 pi, right? So theta equals 2 pi. So those are our two solutions. Theta equals 8 pi over 3, theta equals 2 pi. And we could always check our work by plugging them back in here and evaluating and seeing if it works out. Okay. I mean, for example, look, 2 pi, we know that secant of 2 pi is going to be 1, right? Because cosine of 2 pi is 1. So this just becomes 1 squared plus 1. 1 plus 1 is 2, right? So that was a quick one to check. You could also check your work for 8 pi over 3. I might leave that for you if you'd like. Okay, so go ahead and try these out. I would definitely take some time here, pause, take a break from my voice, okay, and try out a few of these. Get comfortable with the rearranging of the trig equations, particularly the new stuff with the quadratic ones there, okay. Go ahead, give those a shot. If you get stuck on any, feel free to reach out to me, of course. I'm always happy to help. But once you've got a few of those in and you're feeling comfortable, we will move on to talk about general solutions. So right around this time, students often say to me, but wait, doesn't that mean that a trig equation could have like infinitely many solutions? Because we could just keep rotating around and finding more and more angles that have the same ratios and therefore make the equation true? And you're right. That is correct. If the domain is not limited, a trig equation does have an infinite number of solutions. Any angle that is coterminal to one of the solutions is also going to be a solution, right? If our domain had not been limited here, we could have just kept adding 2 pi's and found more and more solutions because they would have the same ratios, right? Again, like if our solution wasn't limited to this domain, wouldn't 4 pi also make secant of theta equal 1? Right? So 1 plus 1 would equal 2, 6 pi, 8 pi, 102 pi, right? All of those would have secant ratios of 1, and therefore they would satisfy that equation. So if theta is a solution to a trigonometric equation, then every single angle coterminal to it will be a solution as well, right? Every angle in the form theta plus its period, meaning going all the way around once, okay, will also be a solution, plus an integer multiple of its period, I should say there, right? So again, if pi over 3 is a solution, then pi over 3 plus 2 pi is a solution. Pi over 3 minus 2 pi again is also a solution. There's infinitely many. We could sit there all day or for the rest of our lives and just come up with more and more solutions, okay? So once you find the solutions in one rotation from 0 to 2 pi, again, these are called principal solutions, the ones from just one rotation, you need to think about all angles coterminal to those. And what we need to do is write an equation for theta to cover all of them for any number of rotations. So for example, just suppose that we found two solutions to a trig equation were 210 and 330 degrees. That actually goes back to the example we did in the previous lesson, okay, to introduce solving, or no, at the beginning of this lesson. Sorry, I'm mixing up my lessons, right? To introduce the idea of solving trig equations, okay? Now, if 210 is a solution, right, notice so will 210 plus another full 360, right? We'll get an angle with the same terminal arm. It'll be coterminal. It's going to have the same ratios. It's got the same reference triangle, all that stuff. So like the sine of 210 is going to be the same as the sine of 210 plus 360, right? What is that? 570, right? Will also be a solution, okay? Same goes in the negative direction. If we rotated in a negative direction like that to get to the same coterminal arm, right? Same terminal arm. That would give us another solution. It's the same terminal arm with the same reference triangle and therefore the same sine ratio, okay? And that would make the equation true as well. So if 210 and 330 degrees are solutions, but we don't have a limited domain and we need to cover all of our infinite rotations, okay? Do we have to write an infinite number of things? Hopefully not, because that would take us literally till the end of time, okay? there's a nice way we can catch all of them, right? To extend this to all angles that are coterminal to 210 and 330, well, we can just say the angles that are coterminal to 210 degrees are 210 plus integer multiples of 360, right? If we're working in degrees, where n is an integer. And that covers all of our bases, right? All of the solutions to this equation will be, well, for the 210 one, will be 210 plus some multiple of 360. Keep in mind it could be negative too, right? Integers include negatives, so it could be 210 minus 360, because that just involves from here you rotate a full 360 in the negative direction to get back to where you started, okay? The angles coterminal to 330, same idea, 330 plus multiples of 360, integer multiples of 360, and if 330 was a solution, that's guaranteed to give us more solutions. So the general solution to this equation would be, here's how you write the general solution. We find it the way we normally would if our domain's not limited and we need to state the general solution to cover all possible angles that could be solutions. We just say, okay, we found 210 as one solution, so the general solution is 210 plus 360n. And we found 330 as another solution, so the other piece of our general solution here is also 330 plus 360n, where n is an integer. So just adding on a little piece here, right? This is all that's new when we talk about general equations, just including all angles that are coterminal to any solutions we've already found. Okay, so another written response from a diploma dealing with these trigonometry, okay? Let's try it out here. So even with written response, it's often a good idea to read the question first so we can get an idea of what we're looking for. It wants us to state the general solution for this equation. Okay, let's see what this equation is that they're talking about. So points A, B, and C are on the terminal arms of angles drawn in standard position as shown below. So there's a point A, a point B, and a point C, and we can see they're showing us that they're on terminal arms of 3 different angles. Okay, these angles are the solutions for theta to a single trigonometric equation. Okay, so it's telling us that whatever these angles are, the angle A, the angle with a terminal arm at B, and the angle with a terminal arm at C, whatever those angles are, they're just the solutions to some trig equation. They're not even telling us what the trig equation is. But they actually don't need to, because remember, all we need to do, all we were asked to do here is state the general solution for this equation, okay? So that state, again, that just means basically tell them. Obviously, we need to show our work, show our thinking. We can't just write it out and say we're done. We should show where we're getting our results from. But state essentially means tell us, right? Tell us the general solution. Show us how you got it, but give us the general solution. So let's take a look here. Well, what angle has a terminal arm that would go through A? Let's just work through them one at a time. Okay, for A, for the terminal arm that goes through A, for lack of a better word. Okay, maybe I'll call it theta A just to show that A is not the angle. A is the point that its terminal arm goes through. Let's think about it. We can see that it's got a reference angle of pi over 4. Okay, reference angle pi over 4. So what is the angle itself? Well, this would be pi, right? This is 0. That would be pi. So theta A there, can you see how it's just going to be pi, take a full pi and subtract pi over 4, right? Pi minus pi over 4. So the angle, right, this angle here, theta A, must be 3 pi over 4, right? 4 over 4 pi minus 1 over 4 pi gives us 3 over 4 pi. Okay, now what it's saying, right, again, is that these angles are solutions to some equation. So we know that 3 pi over 4 is the solution to whatever trig equation it is they're talking about. All they asked us to do is state the general solution. So if 3 pi over 4 is a solution, right, think of it this way. This is a solution. It has the correct ratio to make the equation true. Sure, we don't know what the equation is, but we know that 3 pi over 4 solves it. Well, if 3 pi over 4 solves it, wouldn't that angle that I just drew solve it as well, right? And wouldn't this angle solve it as well, right? It has the same terminal arm. It's going to have the same ratios. So sine of that angle and sine of the one I drew before that and sine of 3 pi over 4 are all the same. So whatever this trig equation is, it's got the same. If 3 pi over 4 is a solution, any angle coterminal to 3 pi over 4 is a solution. And that just means we need to say, in general then, okay, theta could equal 3 pi over 4 plus, what's a full rotation? Well, 2 pi in radians, right? So any multiple of 2 pi, positive or negative, because again, we could also have gone the other way, right? We'll rotate all the way around in the negative direction, and we get back to the same terminal arm. Okay, so 3 pi over 4 plus 2 pi n, where n is an integer. We'll state these all at the end in one nice statement, but that's it. That's all this question is actually asking us to do. So let's do it now for theta b. Whatever angle b is, that would be this angle here, right, to get to the terminal arm that passes through the point B. So what is that angle? Well, that's 180, right? We can see that if its terminal arm goes through B, the only angle that does that in standard position is 180. There we go. Okay, so theta is just 180 degrees there. Whoops, I don't know why I switched to degrees. We're not working in degrees here. We're working in radians. So theta b is just pi. Okay, now general solution time. Pretty quick. The general solution will be pi. Theta could equal pi plus 2 pi n, right? Multiples of 2 pi. If pi is a solution, then so is 3 pi, right? If pi is a solution, then so is negative pi. How do you get from pi to negative pi? You subtract 2 pi, right? How do you get from pi to 3 pi? You add another 2 pi, right? Another full rotation. Okay, I think I actually did 2 full rotations there. Okay, and there we go. So if theta b is a solution to this trig equation, so is every angle coterminal to theta b, right? So theta b is pi, then pi plus 2 pi n is also a solution. So far from this one, from theta a being one of the solutions, we know that all of these angles are solutions. From theta b being a solution, we know that all of these angles are solutions. You can probably see where this is headed. All we got to do now is figure out, all right, what's the general solution that we learn from theta c? Well, what is that angle? We've got 0 or 2 pi, right? We've got pi. Halfway would be pi over 2. Halfway to 2 pi from pi would be 3 over 2 pi. Okay, now we just got to figure out, looks like angle C is in quadrant 4 with a reference angle of pi over 4. So we've got a reference angle of pi over 4, and that means this is our theta C, right? How can we figure that out? Well, did we quite make it to 2 pi? Not quite, right? We stopped a little bit short of a full 2 pi rotation. So let's take 2 pi and subtract pi over 4, right? Which we can think of as 2 pi is like 8 pi over 4 minus pi over 4. So our angle C must be 7 pi over 4. And that is one solution to the equation. They told us that. Whatever this angle is, it's a solution to whatever the equation is, right? But that means that any angle that is coterminal to 7 pi over 4 is also a solution. So multiples of 2 pi, that gives us coterminal angles. Okay, so putting it all together here now, okay, theta could equal, we learned from angle A that solutions could be 3 pi over 4 and any angle coterminal to that. So 3 pi over 4 plus 2 pi n, where n is an element of the integers. We learned from theta b that it could be 180 or pi, right? Pi plus 2 pi n, as long as n is an integer. So pi and anything coterminal to pi. And we also learned that it could be 7 pi over 4 and anything coterminal to that, where n is an integer. Now, this is actually good enough. If you go look at the marking standards for this question, it specifically says that you can leave it as these 3 separate statements. But I do want to point something out, because on like a multiple choice or a numeric where you don't, always get to represent it the way you choose, you have to choose from how someone else has represented it, okay? I do want to point something out here that is common practice with these, is just if any of them can be combined, we like to do that just to make things simpler, right? This is the general solution to this trigonometric equation, right? It is. It covers all of our bases, okay? However, we can combine 2 of these into one statement, because notice this, right? We've got this one, this 3 pi over 4, right? That's the terminal arm of the one that went through A, and we've got the terminal arm of the one that went through C. Now notice, what angle are those 2 angles separated by? What do you have to move through to go from theta A to theta C's terminal arm? It's just 180 or pi, right? It's just separated by pi. So whenever you have 2 angles that are separated by pi, that often means you can combine their general solution parts into one part, right? Look what I mean here. 3 pi over 4 plus multiples of 2 pi gives us solutions. But 7 pi over 4 also is a solution. So we could also just say 3 pi over 4 plus multiples of pi. Do you see what I mean there? Right? Because if I'm here and I add a pi, I get to a solution. If I add another pi, I get another solution. Another pi, another solution. Another pi, another solution. So whenever we have angles like this that are diametrically opposed, we say, diametrically meaning across the diameter of a circle, right? We can combine these 2 general solution statements into one. Because yes, you could go all the way around 2 pi to get another solution, but you can actually go halfway and get another solution. And since you can do that, that means you can go halfway on this side as well and get another solution. So just be aware of that you can see them combined. I'm going to do it here. So I'm going to say that, therefore, our overall general solution is, so we could say theta equals, these 2 can be combined, right? We can combine. So we can say 3 pi over 4 plus pi n, where n is an integer. Be very careful there. If you say plus 2 pi n, then you're leaving out this 7 pi, right? That would go past this one and all the way around. So 3 pi over 4 plus multiples of pi. Now, is there any way to do that with this other one? Pi plus 2 pi n, right? If I just add pi to this, am I going to get another solution? No, right? It doesn't tell us that this terminal arm belongs to an angle that's a solution, okay? So that one, there's really no way to combine it, right? We couldn't just keep repeatedly adding the same angle to this and get back to there. If you're saying, well, why can't we just say, a plus multiples of pi over 4? Sure, the first time you do that, you'll get a solution. If you start from a and add pi over 4, you'll get another solution. But then you add another pi over 4, well, that's not a solution, right? And then add another pi over 4, that's not a solution. Sure, you get one more here, but you're getting a ton that aren't solutions that you would be including as well, right? So it really only works when they're separated by pi. Sometimes you can even get situations where there might be 4 that are all separated by like pi over 2, and then you can combine it even more, right? You could say add pi over 2, add pi over 2, add pi over 2. Then you could just make one statement to cover all 4 principal solutions, okay? But for this one, we're still going to have to state 2 different things. We're going to have to say theta could be 3 pi over 4 plus pi n, or it could be pi plus 2 pi n, as long as n is some integer. And there we go. That's general solutions, right? Add 2 pi's to make coterminal angles. All right, so the last thing we're going to talk about here today, we're going to talk about a couple different kinds, and then we're going to talk about even more in the next lesson, but are things called trigonometric identities, okay? A very helpful tool when working with trig expressions and equations, because what they're going to allow us to do is massively simplify, sometimes to the point where we can make a borderline impossible trig equation to solve, make it actually pretty easy to solve, okay? So let's first, before we talk about trig identities, let's talk in general, what is an identity, okay? An identity is a type of equation, but not all equations are identities, okay? What an identity is an equation that is true for all permissible values of the variable. It's always true as long as what you're putting in, you're allowed to put in. Okay, so notice the difference there. It's not just an equation where, there might only be certain values of x that make it true. It really is always true. So just for a simple example, we could call this an identity. 1/2 of x is equal to x divided by 2, right? That's true no matter what x is. Multiply something by 1/2, that's the same as dividing it by 2, right? If x is 4, 5, 6, negative a billion, no matter what number you dream up to put in here, it's always true. That's an identity, right? Compare that to, something like x plus 1 equals 5. That is true for one value of x. It's true when x is 4. It's certainly not true for all values of x. So this is definitely not an identity, okay? So what makes an identity is that it's true no matter what value of the variable you put in. Okay, that makes it an identity. So a trigonometric identity is just one that you can probably guess involves trig ratios. You've actually already seen several trig identities, but here's one example. Remember this from the previous lesson, right? Tan x is just equal to sine x over cos x. That really comes from, it's not just made up magic rule. It comes from thinking about, well, tan is opposite over hypotenuse. On the unit circle, we know that since r is 1, right? Sorry, I'm just going to draw this a bit bigger, right? Since r is 1 on the unit circle, then cos x is just going to be the x coordinate. Whoops, I went a little too far there, right? This is cos x, this is sine x. So what's tan x, right? Well, opposite over adjacent. Sine x over cos x. Tan x would be sine x over cos x. That's true for all values of x. It's an identity, okay? Now, this is true for pretty much all values of x, but there are, I should say, some exceptions. And it's not that it becomes untrue, it's that it becomes undefined. Okay, so it's not like there are exceptions to tan x equaling sine x over cos x where sometimes it comes out to give you that's not true. Otherwise, it wouldn't be an identity. It's just that there are some values of x that make the whole thing undefined. There are non-permissible values for x in this identity. We have non-permissible values whenever we divide by zeros, so it's asking us to determine what are the NPVs for that trig identity. Well, for tan x equals sine x over cos x. We're dividing by cos x. So that tells us we're going to get NPVs, okay, where cos x equals 0. NPVs are x's that make cos x equals 0, right? We're just saying cos x can't be 0 because then we'd be dividing by 0. Cos x cannot equal 0. So that just turns this question then into, well, what values of x make cos x equal 0, right? Well, we know that. We know that cos is 0 at 90 and 270, right? Wherever the adjacent side, wherever our x coordinate of a point on the terminal arm would be 0. So that happens here and here, where a point on the terminal arm could be 0, 1, or 0, -1, right? So at 90 and 270, or at pi over 2 and 3 pi over 2, right? So x cannot equal, what did I just say? Oh yeah, pi over 2 and 3 pi over 2, right? Or 90, 270, okay? But there's more than that, okay? Because it's not just 90 and 270, it's also 90 plus 360 and 270 plus 360 or 270 plus 720, right? Full circles are going to get us back to cos x equaling 0. So we have to include all of those, okay? So let's just say x cannot equal pi over 2 plus 2 pi n, where n is an integer. X cannot equal 3 pi over 2 plus 2 pi n, where n is an integer. Hey, could we maybe combine those, right? If I start from pi over 2, could I just say, well, adding pi will get us to 3 pi over 2. Adding another pi gets us to 5 pi over 2. Another pi gets us to 7 pi over 2, right? Notice these are just separated by 180, or pi. So we could actually simplify these. We could combine. They're separated by pi, so we can combine into one statement. We could just say x cannot equal, let's say, pi over 2 plus multiples of pi. Okay, x cannot equal pi over 2 plus any multiple of pi. That covers all of our bases because there's that angle, right? Go from here, add pi, you get another NPV. Add another pi, you're back to another NPV. Add another pi, you're back to another, and on and on. Okay, so there we go. Those are the non-permissible values for this trig ratio, this trig identity, okay? And notice, that makes sense, right? The reason tan x, we know that tan x is undefined at pi over 2 and 3 pi over 2, and any angles coterminal to that. Well, now we have a deeper, or at least another way of explaining why, because tan x is equivalent to sine over cos, and cos becomes 0 at pi over 2 and 3 pi over 2, and any angle coterminal to those, giving us a division by 0. So yet another way we can kind of pick apart why it makes sense that tan x would be undefined if x is pi over 2, 3 pi over 2, or any angle coterminal to those. All right, so let's take a look at some identities, some more identities anyway, because that was also an identity. The reciprocal identities, you know these ones, they're just the definitions of the reciprocal trig ratios. By the way, all of these identities, including this one, all the ones we're talking about here, they are on your formula sheet. You're going to want to have that handy, especially when we do the next lesson and we get some more complicated identities. These are really nice to have to be ready to reference when needed. Okay, so these are just the definitions of the reciprocal trig ratios. They hold, they are true, no matter what x is. That makes them identities. Okay, they are always true. Now, that being said, there are non-permissible values. So again, it's not like that makes it untrue, but it does make it undefined. So can you see the values of x that would be non-permissible values for these, right? Does cosecant x have NPVs? Well, look what we're doing. We're dividing by sine of x. So for cosecant x, we know that sine x can't equal 0. Otherwise, we'd have 1 over 0. That's undefined. So when does sine x equal 0? When x is 0 or pi or anything coterminal to those, right? Because then the opposite arm of our reference triangle is 0. So sine of pi or 0 or anything coterminal to them is 0, which would make cosecant x undefined. It would be 1 over 0. Lost my train of thought for a second. Okay, so sine x cannot equal 0, so x cannot equal 0, pi, or anything coterminal to those, right? So as a general solution, we could say that our NPVs, shouldn't call it a solution, it's not a solution, but to cover all of the NPVs, we could say x cannot equal, well, once again, they're separated by pi. So we can actually combine into one statement again, right? Starting from 0, add pi, you get an NPV. Add another pi, you get another NPV. Add another pi, you get another NPV. So x cannot equal, it's actually just multiples of pi, right? You could say 0 plus pi n if you want, but that's ultimately saying the same thing because n is an integer, so it could be 0, right? X cannot equal multiples of pi, integer multiples of pi. All right, for secant x, well, we're dividing by cos x, right? Secant x is equivalent to 1 over cos x. So cos x cannot equal 0, right? We actually just established in the previous example there that that means x cannot be, right? Cos x is 0 when x is pi over 2, or 3 pi over 2, or anything coterminal to them. So if you're okay with it, I'll just reuse that from the previous question. We already know how to make cos x equal 0. It happens at pi over 2 plus integer multiples of pi. There we go. Now 1 over tan x. So, right, 1 over tan x means that we can't be dividing by 0. So where is tan x equal to 0? Where does tan x equal 0? Well, if we think about it, once again, it's opposite over adjacent, right? Or y over x if we're still thinking about, the reference triangle and its y part and its x part. So where is the y coordinate 0 for our reference triangles? It's at 0 and pi, right? It's actually the same as sine x. That makes sense because tan x equals sine x over cos x, right? So wherever sine x is 0, tan x will also be 0, okay? So we already said that, right? We said where that happens. It's at 0 and pi. So x cannot equal multiples of pi, right? Integer multiples of pi. Okay, now this actually, look, this makes a lot of sense too. Look, 1 over tan x, cotan x is, well, that's 1 over sine x over cos x, right? And dividing by a fraction is the same as multiplying by the reciprocal, so this is the same as cos x over sine x, right? Shows us that cotan x, which, by the way, this is another identity on your sheet. It's just flipping the sine x over cos x, because that's what cotan of x does. So cos of x over sine of x, right? Notice, yeah, sure enough, looks like sine of x can't equal 0 if we want to talk about cotan of x, right? And we know sine of x equals 0 at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, multiples of pi, okay? All right. The next one, again, we've kind of just talked about them quite a bit here, but these are the quotient identities. You've seen these. They just come from the unit circle, right? These are relationships that we've been talking about. Since r is 1 on the unit circle, and sine theta equals y over r, and cos theta equals x over r, we can see that sine theta is y, and cos theta is x. Then, since tan theta is y over x, and cotan theta is x over y, right? Well, again, right? Again, just visualizing that. If we're thinking about the unit circle, this has a radius of 1. This is x. This is y. Then opposite over hypotenuse, right? Y must just, like, sine theta is y over 1. So sine theta is y, right? This is just sine theta. Adjacent over hypotenuse, x must just be cos theta, right? X over 1 tells us that cos theta is just adjacent over hypotenuse. X over 1, x is cos theta, okay? And then if we think about tan theta, opposite over adjacent. If we think about cotan theta, adjacent over opposite. So that's where these come from, okay? Tan x is just equivalent to sine over cos. Cotan of x is cos of x over sine of x, okay? And you can see that each of these will have their own non-permissible values. We just kind of talked about them in that one, so I won't go too far into it. But again, these are identities. They're true no matter what the value of x is, no matter what angle we're thinking about taking the ratio of, so long as that angle is permissible, as long as it doesn't give us something undefined. Okay, so what's the big deal with trig identities? I touched on it earlier, but what they allow us to do is massively simplify expressions or equations. They can even let us rewrite equations that would be pretty much too impossible to solve in very easily solved formats. And by rewriting parts of an expression or equation using things they are equal to via an identity, we can often combine several things into one or even cancel them out completely. Okay. And all of these identities, I know, like, at first they sometimes seem like maybe not these ones because we just talked about where they all come from, but they all just get derived from basically looking at ratios on the unit circle and seeing, okay, can we come up with any relationships that we can see will always be true? It honestly mostly comes from things like, SOHCAHTOA and Pythagorean theorem. That's where most of them come from, because we're looking at triangles within the circle, the unit circle there, and finding ratios and looking for relationships that we can say, okay, well, if this equals that, then that has to equal this. And that gives us these nice handy relationships that we can rely on to simplify and analyze trigonometric equations. Okay, let's try some of these examples out where we employ these trig identities. All right, quick tip right off the bat that is going to apply for lots of trig identity stuff. It's not always 100% the number one move you should make, okay? But it's kind of one of those things that's like, hey, this might be a good idea, like most of the time. So when simplifying trig expressions, one of the first strategies that should often be employed, I won't go as far as saying it should always be employed, but like I'd even say 99 times out of 100, or maybe 95 times out of 100, that's probably a good move. It's never something you'll regret doing, okay, is rewriting everything in terms of sine or cosine. And the reason for that is that most of the identities are written in terms of sine or cosine. And so if we rewrite stuff that's not sine or cosine, that can allow us to see where things could cancel out, right? So that's where massive simplification can happen. All right, let's try these two out. It wants us to simplify each of the following expressions and state any non-permissible values. Now, our non-permissible values here, they can come from basically two places, right? NPVs that are just part of that trig ratio, like tan x, for example, we know is undefined at 0 and pi, right? And anything coterminal to that. But they can also come from like divisions within the ratio itself, right? Within the expression itself. For example, here, secant x now, we can see, well, that's not allowed to equal 0. So whatever values of x make secant x equal 0, those are non-permissible values, right? Same here. Whatever would make cotan x equal 0, that's a non-permissible value because we'd be dividing by 0. Okay, so the non-permissible values are also much easier to see when we go ahead and write everything in terms of sine x and cos x to start out with. So let's try it out. Cosecant x, well, that's just, we're going to first rewrite everything in terms of sine and cos. So cosecant x is 1 over sine x. Cotangent x is cos of x over sine of x. Secant of x is 1 over cosine of x. And sine of x is, well, just sine of x. So notice all I did there was this. I rewrote everything in terms of sine or cosine, right? The reason being, like, we know that tan is sine over cos. We know that, like, cosecant is 1 over sine, and secant is 1 over cos. So if I rewrite, and cotangent is cos over sine. If I rewrite anything that's tan-y in terms of sine and cos, I can probably cancel something out, or simplify at least, with the other stuff that's got sines and coses. Okay, so with that in mind, let's actually, before we start canceling out, we need to state our non-permissible values. Okay, we don't want to simplify everything and cancel out and then come back and state our non-permissible values because we might have lost stuff, right? For example, this cos of x is going to cancel out. We can see that, right? But it's still here, right? It's still in the equation. We are dividing by cosine of x. So we can see that our NPVs, pre-simplification, cos of x cannot equal 0. And also we're dividing by sine of x, so sine x cannot equal 0. Be very careful. Common student mistake is to say, there we go, I stated my NPVs, but cos x isn't the variable. X is the variable, right? So we need to state, if cos x cannot equal 0, that means x cannot equal, well, where does cos x equal 0, right? When we're on the y-axis with our terminal arm. So that's at pi over 2, 3 pi over 2. Okay, and on and on and on, right? Anything coterminal to those. For this one, where does sine x equal 0? Well, whenever our terminal arm is on the x-axis, right? That makes the opposite part equal 0. So that happens when x is 0 and pi and 2 pi, etc. Okay, Anything else for NPVs? I don't think so, because all we're dividing by here is sine x and cos x, right? There's not like another division that's just part of the expression either. So I think for our NPVs, that's a good start. Can we simplify this a bit though? Right, if we list out our NPVs here, look what we've got in one rotation. 0, pi over 2, pi, 3 pi over 2, 2 pi, right? And then anything coterminal to those. So the next one would be 5 pi over 2, then 3 pi, right? Then 7 pi over 2, then 8 pi. Wait, I skipped one. 4 pi, right? So it looks like it's actually just, right? If we draw these out, maybe it'll make it even more obvious. 0, pi over 2, pi, 3 pi over 2. We could actually simplify this to one statement. X cannot equal pi over 2 n, right? Or n pi over 2. It's just multiples of pi over 2. Every time we rotate pi over 2, we get to another NPV. It's just the quadrantal angles and any angle coterminal to the quadrantal angles. So x cannot equal pi over 2n, where n is an integer. There we go. There's our NPVs. Okay, now let's get back to the main thing they asked us, which was to state any non-permissible value. Or sorry, that's what we just did, was to simplify was the main thing they asked us. So just look here, right? What can we simplify? I mean, if it helps you, you can multiply it all together. 1 times cos times 1 times sine gives us cos x times sine x over sine x times cos x. You could combine that sine x times sine x into sine squared of x, but I'm just noticing that we've got a sine of x in the numerator. We can cancel that out. Sine of x over sine of x is just 1. And then look at this. Cos of x over cos of x is just 1. And so what we're left with is just 1 over sine of x, which is just equivalent to cosecant of x. So look at that. That big kind of scary looking thing was actually just equivalent to cosecant of x. Can you see why trig identities might end up being super helpful for simplifying, right? Would you rather solve, this equals 0, or would you rather solve something like cosecant of x equals 0? The power of trig identities is that they let us see that this is actually equivalent to this by simplifying. Okay, let's try part B here. All right, now for this one, you're probably noticing, and that's good, right? We are dividing by this stuff. So secant x and cotangent of x also cannot equal 0, right? However, we'll still catch those if we turn everything into sine of x and cos of x first. Personally, I find that a little bit easier to see, right? Like, what exactly are we dealing with? So let's just first do that. I'm going to first turn everything into terms of sine of x and cos of x. So tan of x we know is, sine of x over cos of x. That's being multiplied in our numerator by cos of x. In our denominator, we've got secant x, which we know is 1 over cos of x, times cotangent of x, which is the reciprocal of tan, right? So if tan is sine over cos, cotan is cos over sine. Okay, now let's get back to our NPVs, okay? The reason what I said there was that it's a little bit easier, I find anyway, to see all the places we could get non-permissible values if we first just write everything in terms of sine and cos. You definitely could do it. You could, look here, but it's easier to miss some this way because we would recognize, now we can recognize that, oh yeah, yes, we're not allowed to divide by 0, so secant of x can't be 0, but also secant x itself is a division. It's 1 over cos of x. So that is another NPV, right? Cos of x is not allowed to equal 0. Same thing here. Yeah, cotan of x can't equal 0. But also from this, we learn that sine of x can't equal 0 because this is a division. We're doing cos of x divided by sine of x. So that's one we might have missed, right? If we just said cotan of x can't equal 0, we might have missed that also sine of x can't equal 0. So like I said, there's basically two places you can get these non-permissible values from, like actual division within the expression. So that's here, we can't divide by 0, right? But also within the ratio itself. Okay, now we already knew cos of x couldn't equal 0, but be careful. Even if this weren't here, just pretend for a second that this weren't here, or actually that this weren't here too, right? Cos of x still would not be allowed to equal 0, even if we're imagining those aren't there. Do you see why? We're dividing by cos of x over sine of x. If cos of x were 0, this would be 0, and we'd be dividing by 0. So just be careful about that, right? We can get an NPV from the fact that we're dividing by cos of x too, right? And in that case, we'd be dividing by 0 if cos of x were 0. Now, in this case, we probably would have been safe because we already knew we couldn't divide by 0, cos of x couldn't be 0, and we extra knew from here that cos of x couldn't be 0. But there are actually three things here, three separate things that all tell us cos of x cannot equal 0. So for our NPVs, we are definitely very confident that cos of x cannot equal 0. And since we are doing a division by sine of x here, right? Yes, it's in a denominator, but this is still a division, cos of x over sine of x. We also know that sine of x cannot equal 0. Okay, so that's actually the same thing we had in this one. So if you're okay with it, I'll just recycle that. So x cannot equal multiples of pi over 2, right? Either cos of x or sine of x is 0 at each of the quadrantal angles, and all angles coterminal to the quadrantal angles. All right, now let's get back to simplifying this thing. Okay, now there are many approaches we can take, especially in the next lesson where we learn even more of these trig ratios. There's never really one correct approach, but let's just start out, see if we can cancel anything. Like for example, sine x over cos x times cos x. Well, those cos of x over cos of x, those can just cancel out. And actually, a similar thing is happening in our denominator. We have 1 over cos of x times cos of x. So those cos of x over cos of x is just 1 as well. So we're going to have sine of x over, what are we left with in the denominator? We're going to have 1 over sine of x. Now, dividing by a fraction is the same as multiplying by its reciprocal. So dividing by 1 over sine of x is actually the same thing as multiplying by sine of x over 1, giving us sine of x times sine of x, which is sine squared x. And there we go. So this just simplified to sine squared of x. Cool, right? I find these very satisfying when they start out very complicated and they simplify to a nice, easy thing. Okay, let's try this one out. So it's one from an old release diploma. Okay, let's take a look. The non-permissible values for the identity cosecant x tan of x equals secant of x are... Okay, so a lot of these identities, again, I know they seem kind of weird, like even these. A lot of them do come from looking at relationships and just saying, hey, how are these things related to each other by playing around with the triangles and the ratios on the unit circle. Pretty cool. Okay, anyway, though, let's see if we can figure out. Now, like I said, I find it a lot easier to identify what's going to be an NPV if we just first take that step of rewriting everything in terms of sine and cos. So let's do that. Cosecant x. How can I rewrite that in terms of sine or cos? Well, cosecant is just 1 over sine, right? So this is just 1 over sine of x. Times tan of x. Well, tan x is just sine of x over cos of x, right? And that equals secant of x, but secant of x is just 1 over cosine of x. And see what I mean? It's now a lot easier to tell what exactly we're working with when it comes to what are we not allowed to divide by, right? Or rather, what are we not allowed to make x so that we are not dividing by 0? And so now we can see, right? Take a look. Our NPVs are going to come from the fact that sine x cannot equal 0, or we'd be dividing by 0 here. Cos of x cannot equal 0, or we'd be dividing by 0 here. And we already covered it, so we don't necessarily need to say it again, but same thing here, right? If this had not been here, cos of x still could not equal 0 because then we would be dividing by 0 there. So sine of x cannot equal 0, cos of x cannot equal 0. Okay, so we kind of talked about that all in the last two examples. That's where our NPVs came from as well. Just be aware, it's not always going to be those ones. These examples just happen to have it was true that sine of x couldn't equal 0 and neither could cos of x, okay? But again, what angles, what x's would make sine of x equal 0? Well, wherever the opposite side on our reference triangle, right, the y-coordinate, would equal 0. So that's at the x-axis, at the angles 0 and pi within one rotation, right? Where would cos of x equal 0? Well, wherever the adjacent, the x-coordinate of a point on the terminal arm is 0. So that's at the y-axis. That's at pi over 2 and 3 pi over 2. Now, this goes back to my point earlier, right? Is it fine to say that, x cannot equal pi over 2 plus 2 pi n is an integer? X cannot equal pi plus 2 pi n is an integer. And on. Do it for 3 pi over 2. And then do it for, what am I missing? Oh, that's all of them. Sorry. Right? Is it okay to say that? Sure. Right? That is fine. However, on like a multiple choice type numerical one, like we have covered them all, but recognize that like if you've ever done it and you're saying, oh, they didn't list 3 different things, it's possible they just combined them because it's pretty easy to combine these once we take a look and realize what's going on here, right? It's just 0, pi over 2. Oh, I did miss one. I missed the first one we said. X cannot equal 0 plus 2 pi n, right? It's just 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, right? It's just multiples of pi over 2. So we can combine these into x cannot equal pi over 2 times n, where n is an integer. Integer multiples of pi over 2. So that looks like, it looks a little bit different than how we wrote it, but c, right? N times pi over 2, where n is an integer. So there we go. Those are the NPVs for that expression. All right, let's talk about another type of identity, Pythagorean identities, and that will be it for this lesson. All right, so the Pythagorean identities are up next, okay? And as the name suggests, these just come from applying the Pythagorean theorem, okay? Applying it to what? Well, to right-angle triangles along the unit circle. Any right-angle triangle along the unit circle. Because again, any reference triangle that we draw along a circle that is centered at the origin is going to have these side lengths, right? If I take a circle, sweep out an angle with a radius r, right? Then it has some x-coordinate and some y-coordinate at the point where that terminal arm of the angle intersects with the circle that I'm sweeping out while I make my angle, right? And on the unit circle, we can see, before we get to the unit circle, with the Pythagorean theorem, right, we can see that the equation of the circle is just x squared plus y squared equals r squared, right? There's our little triangle. Pythagorean theorem tells us a squared plus b squared equals c squared. So for a triangle like this, the x-coordinate squared plus the y-coordinate squared will give us the radius of the circle squared. Now, let's make our lives easy. This technically works. This relationship works on any circle, but our life gets a lot easier if we just use the unit circle where r is 1, right? Because 1 is a really nice number to work with. And so if we use the unit circle, we know that r is 1, x is just cos theta, right? Because adjacent over hypotenuse is just x over 1. So x must be the same thing as cos theta. Opposite over hypotenuse, sine theta, is just going to be that y-coordinate over 1. So sine theta is just the same as our y there if we're on the unit circle. Okay, that's where we got that idea that, any point that's on the terminal arm of an angle and also on the unit circle, that point's x-coordinate is just cos theta and its y-coordinate is just sine theta. So if we apply the Pythagorean theorem here, we can see that we would have cos squared of theta plus sine squared of theta equals 1. This is the Pythagorean trigonometric identity. It's just that the cos squared of an angle plus the sine squared of an angle will always equal 1. And that's it. That's where it comes from. It's just the Pythagorean theorem applied to a triangle along the unit circle. It's incredibly powerful. But we can see that it's always true. It's an identity, right? No matter what angle we think about, that's going to be the case, right? If I did it for this angle here, this would still be 1. This x coordinate would just be cos theta. this y coordinate would just be sine theta, right? And no matter what, no matter where we imagine drawing this angle and thinking about the reference triangle, cos squared theta plus sine squared theta will equal 1. So this is the basic form of the Pythagorean trig identities. Here are all of 3 of them. Don't panic. Okay, I know the other 2 don't seem quite as obvious. They actually just come from doing some simple algebra. I mean, they also can come from like thinking about different relationships within this situation here, looking at things like cotans and cosecants and secants, okay? But they also, what you can look at them as coming from, because they are from this as well, is if we just divide both sides by something, we can come up with these 2. So if I take this and I divide both sides by sine squared of x, I will get this identity. If I take this thing and I divide both sides by cos squared of x, I will get this identity. So they really are all equivalent. We've just rewritten them in terms of a few other variables, a few other ratios, just to have, more tools in our kit. So when you look on your formula sheet, you will see all of these there, right? These are all there. They're really all the same identity. They're all just the Pythagorean identity. But to be able to deal with, okay, but what if our equation doesn't have a sine squared and a cos squared? It has a tan squared and a secant squared. We give you all 3 of these so you can just more quickly recognize it. And then you don't have to... Sorry, video got cut off there. And then you don't have to do this on your own, right? I mean, you could. You're capable of dividing both sides by sine squared or dividing both sides by cos squared, but they decided to be nice and give you these 3 forms on the formula sheet. Okay, so just to prove that to you really quickly here, right? Notice this one, right? Where does it come from? I'm claiming that it just comes from dividing both sides by sine squared of x. Well, look, if I took cos squared and divided by sine squared, if I did cos squared over sine squared x, and then I'm going to divide both sides by sine squared, right? Equals 1 over sine squared. I just took this and I divided both sides by sine squared. Well, cos over sine, that's cotan, right? Cos over sine is cotangent. So this is cotangent squared x. Sine squared over sine squared is 1. And 1 over sine squared, well, 1 over sine is cosecant. So 1 over sine squared is cosecant squared x, right? Hey, same thing, right? So it really is, it's just sine squared plus cos squared equals 1, but it's what we get if we play with it a bit and say, okay, are there any other relationships we can pull out? If we divide both sides by sine squared, we get this one out, okay? Same thing for this one, but if you divide both sides by cosine squared x, right? I maybe won't show all my work for it, but just talk through it with you. If I divide cos squared by cos squared, I get 1. If I divide sine squared by cos squared, sine over x is tan, so I end up with tan squared x. And if I divide 1 by cos squared x, well, 1 over cos is secant. So 1 over cos squared x gives us secant squared x. So they're really the same identity, just kind of played around with in 3 different ways so that we can use them in different situations more conveniently. Okay? Now, the Pythagorean identities are very handy. If you ever see that any of the trig ratios are being squared in an expression, it is always, always, always worth a shot to check, to at least look if you can use one of these identities to simplify. If you're working with something and you see a tan squared or a, cotan squared or a secant squared or a cos squared or whatever it is, it's always worth a second to see if you can use any of these to simplify. Okay, now, just a note here, these are how they're written on your formula sheet, but keep in mind, we could move stuff around this equation. So these could be arranged in many different ways. It doesn't have to exactly match the form you see on your formula sheet to be useful. In fact, that means it's useful in many more situations. For example, if you saw something like, 1 minus cos squared x, right? Well, we could replace that. If we look here, can you see how that's just equivalent to sine squared x, right? Because if sine squared x plus cos squared x equals 1, well, then subtract cos squared x from both sides, right? So 1 minus cos squared x is just the same as sine squared x. So just be on your toes. Be aware that it's not like if it doesn't have this exact form, you can't use it. In fact, that means you can use it in many more situations, right? If you see a 1 plus tan squared, well, I mean, that's just the base form. But if you see a secant squared minus 1, well, that's actually just going to be equal to tan squared. So whenever you see a trig ratio being squared, take a second, pause, pull out your formula sheet, and see if one of the Pythagorean identities can help you simplify. Okay, let's try simplifying some out that involve potentially some Pythagorean stuff and also the reciprocal or quotient ones we talked about earlier. All right, so what I've done here, I've just pulled, this is from your formula sheet. This is part of the identities. There's more below it that you'll see. We'll talk about those ones tomorrow, okay? But always a good idea whenever working with trig identities or, trig in general, I guess just when you're doing math, good to have your formula sheet nearby, okay? But that's especially true here because we want to, look for inspiration, right? We can look here and see, okay, is there anything I could see that maybe I could use, okay? So we want to simplify this one, tan squared x plus 1 over secant of x. So I see that tan squared, okay? That squared makes me think, okay, let's see if maybe there's a Pythagorean identity I can use to try out to see if I can simplify it, right? Because replacing tan squared x plus 1 with, hey, 1 plus tan squared theta, that's the same as tan squared theta plus 1. It's equal to secant squared of theta. So that means this is just equivalent to, this numerator is just secant squared of x, right? Now, even planning ahead a little bit, that's going to be really nice because it's over secant x. So those are going to cancel out. So do you see what I mean here? Like when I was saying earlier, it's often a good idea to rewrite everything in terms of sine and cos, yes. But sometimes students hear that and they get like really focused in on it and it's all they ever do. Don't forget there's other relationships we can take advantage of as well, right? In this case, rewriting everything in terms of sine and cos might have actually made things a little trickier as our first step, okay? So don't be too much of a robot and just go, okay, sine and cos, right? Good idea to check for Pythagoreans as well and that kind of thing first, because sometimes that can make things even simpler. So now we know we can write this as secant squared of x over secant of x. And hey, secant squared of x, that's just secant of x times secant of x, right? And we're dividing it by secant x, so that's just, right, the squared can cancel. This actually just equals secant x, right? So all I did there, I saw this tan squared of x plus 1. I thought, ooh, that seems kind of Pythagorean. Went to my formula sheet, said, oh yeah, 1 plus tan squared theta is secant squared theta. So tan squared x plus 1 is just secant squared x, and then that means we have secant squared x over secant x. That simplifies to just secant x. Cool, right? They didn't ask us for NPVs here. We could state them, but in the interest of time, let's just move on to this one here, okay? All right, so looking at this one, I see tons of stuff that looks pretty Pythagorean identity-ish, right? Like 1 plus tan squared x. Well, hey, 1 plus tan squared x, if we reference our formula sheet with all the identities, that's just secant squared of x. So I'll just kind of make note of what I'm going to do here. I'm going to rewrite that as secant squared of x. Cotan squared of x plus 1. Cotan squared of x plus 1. Aha! That's just equivalent to cosecant squared of x. And again, that seems like a really nice replacement to make because then cosecant squared divided by cosecant, I can make some simplification, right? So remember, our goal here is to simplify. So often we can kind of say, sometimes we can plan ahead a little bit and say, will this help me make things simpler? Okay. Now, this secant cubed of x, this is, like you can think of secant cubed as secant squared times secant, right? So we maybe might think of using this one possibly there. But if we're thinking ahead a little bit, I have a secant squared up here that could end up canceling out with this pretty well, so I might actually just leave this as secant cubed. Now, remember what I said, there's not one right way to do this. You might also have noticed that secant cubed is secant squared times secant, and then rewritten that secant squared as 1 plus tan squared x, and been able to cancel it out with this one instead, and left that one alone. So I want to be clear here, there are lots of approaches we can take, lots of different things we can do. Okay, now, If you're thinking cosecant, could we write that as 1 over sine? We could. Could we write this as 1 over cos? We could. But I'm just going to see what this does for us because I can already see a lot of cancellation, right? And we can always keep working on it after if if we think we can go simpler. So this is going to give us secant squared x. I'm rewriting 1 plus tan squared as secant squared. Cotan squared plus 1, I said I was going to rewrite as cosecant squared of x. And then we're dividing that by secant cubed of x times cosecant of x, right? And think about what this is really saying. It's secant times cosecant divided by secant times secant times cosecant, right? So secant squared x here. Just to really drive the point home, let me just write it all out. Of course, we normally don't have to do this, but just to really show you the simplification here. Whoops, cosecant squared of x times cosecant squared, cosecant of x times cosecant of x. Secant cubed is just going to be secant x times secant of x times cosecant of x. So all I'm doing there is just actually showing the squaring and the cubing just to really hone in on what we're canceling. So secant x over secant x is 1. Secant x over secant x is 1. Cosecant over cosecant x is 1. And this leaves us with cosecant of x over secant of x. And now this is where I might say, okay, can we simplify this more, right? And this is where I would say, okay, now it might be time to rewrite stuff in terms of sine and cos, because again, all of these type of ones, like I know I'm dividing stuff. I'm dividing a cosecant, which has to do with sine, and a secant, which has to do with cos. So it's not super obvious, though, exactly what we're doing there, right? And that's why I said, since most of those, especially the quotient identities, are written in terms of sine and cos, this is where it might be a good idea now, okay, let's rewrite this in terms of sine and cos and see if we can simplify it using our quotients identities possibly. So cosecant of x is just 1 over sine. And secant x is just 1 over cos. So we have 1 over sine x divided by 1 over cos x. Well, remember, dividing by a fraction is the same as multiplying by its reciprocal. So this is the same as 1 over sine of x times cos of x over 1, which means it's just cos of x over sine of x, which means cos over sine, that's just cotangent, right? That's just cotangent of x. So hopefully this example gets at what I mean. Yes, rewriting in terms of sine and cos is a great strategy, right? We probably wouldn't have noticed that this was cotan of x without doing that, okay? So it's never a terrible idea or anything. But when we can use a Pythagorean as well, and like the Pythagorean is right there, ready to go, then it's probably a good place to start there for that one, right? Because we can see that we can cancel immediately. So we've got our Pythagoreans, we've got rewriting in terms of sine and cos to make use of the quotients and the reciprocal identities, okay? We'll see even more strategies in the next lesson. Okay, all we got left here is one release diploma question dealing with these Pythagorean and or quotient identities, and that will be it for this lesson. All right, so what are we doing in this one from the diploma? Let's just see first, and then we'll look at the info. Using the expression numbers above, arrange the trig expressions from lowest value to highest value. Okay, so we're going to be ordering these from highest to lowest. Let's just see. Each of the following trig expressions can be simplified to a numerical value, meaning just a number, right? So they're saying that this can be reduced to just a number. And same for this one and same for this one. Then we're going to use these to order them from which one's the biggest to which one's the smallest. Okay, and then it's stating where cos theta cannot equal 0 and sine theta cannot equal 0. Those are the NPVs of these situations, right? I mean, we can see like tan, we've got sine over cos, so cos couldn't equal 0. Dividing by sine here, so sine couldn't equal 0. It's just clarifying that those are the NPVs for these expressions. Okay, let's jump in here though. Which one makes more sense to start with? The number 1. So let's look at expression number 1 over here. Okay, we've got tan squared theta minus secant squared theta minus 1. let's pull out our list of identities. Maybe I'll just bring this over here so it's a little bit closer. Okay, for a real formula sheet, we could just pick it up and look at it. So tan squared minus secant squared. That's definitely making me think Pythagorean, right? Like tan squared, tan squared and secant squared. So we might have to get a little creative here, but tan squared minus secant squared, can we see how this could be rearranged to be helpful there, right? If 1 plus tan squared theta equals secant squared of theta, well, what is tan squared of theta minus secant squared of theta equivalent to, right? We know that 1 plus tan squared of theta equals secant squared of theta. So can we play around with this to make it look like that and see what it's equivalent to? I think we can, right? If I subtract secant squared of theta from both sides, I'll have tan squared minus secant squared on this side. And then if I subtract the 1 over, let's just see what happens. I'll have tan squared of theta minus secant squared of theta equals, subtract 1 from both sides, equals -1, right? So this is actually just equal to, right? This is really just, yes, tan squared minus secant squared, but we can show with this identity that tan squared minus secant squared is just equivalent to -1. So this is actually just -1 minus 1, which is -2. So expression number 1, this is just equivalent to -2 when we simplify using our trig ratios, or our trig identities, sorry. Okay, so that's good. 1 down, 2 to go, and then we've got to use these numbers to say, like if this one ends up being -1, we know that -1 is greater than -2. So that helps us start getting our order set. So let's move on to number 2 then and see if we can simplify that down to a numerical value like we just did with number 1, right? We simplified it down to just -2. So let's do expression 2 now. We've got tan theta cos of theta over sine of theta. Okay, now this one here, I don't see any Pythagorean stuff we could really pull out. What we can do though, and what's never really a bad idea, is to rewrite in terms of sine and cos. So let's just take that tan and rewrite it as sine over cos, right? Again, that is one of our identities. It's one of the quotient identities, we call them. So this is just sine of theta over cos of theta times cosine of theta over sine of theta. Okay, so what does this simplify to? Well, sine of theta over cos of theta times cos of theta. Can you see that those are just going to cancel out, right? That just equals 1, cos of theta over cos of theta. So we're just left with sine of theta over sine of theta, right? And sine of theta over sine of theta is just 1. So expression 2 ends up just simplifying to a numerical value of 1. That literally is equivalent to 1. And it's true for all permissible values of theta, right? I mean, you can try it out yourself. Pick any angle you want. Do tan of 30 times cos of 30 over sine of 30. It'll tell you 1. Or you could do the math yourself there with your special angles and see that it equals 1, right? It actually works for any angle. We'll talk about proving that in the next lesson. Okay, let's do the third one then. So far we know that expression 2 is equivalent to 1. Expression 1 is equivalent to -2. So far our order would go 1 is less than 2, but we still got to see where 3 fits in. So let's look at expression 3. Expression 3 is secant of theta minus cosecant of theta over the cotangent of theta. Again, nothing really Pythagorean looking here that we might be able to simplify with. So let's just go ahead and rewrite in terms of sine and cos and see if we can simplify any there. Okay, so secant of theta, well, that's just 1 over cosine of theta. Cosecant is 1 over sine of theta. And then cotangent, we're dividing cosecant by cotangent, and cotangent is just cosine theta over sine of theta. So this is over cosine of theta over sine of theta. All right. just to kind of see what we got, what we're working with here, let's just maybe rewrite that division by a fraction as multiplication by the reciprocal. So that's going to leave me with dividing by cos over sine is the same as multiplying by sine over cos. And then, hey, look at this. Cos sine over sine, right? That's just 1. So we end up with 1 over cosine of theta minus 1 over cosine of theta. Doesn't matter what theta is, that's going to equal 0, right? 1 over cosine of theta minus itself, it equals 0. So this one just ended up equaling 0. All right, so we did it. We're feeling pretty good about this because it said we could simplify them all to a numerical value, and we did. So the first one was equal to -2, the second was +1, and the third was 0. So now it wants us to use those expression numbers to arrange them from lowest value to highest value. So the lowest of these three is -2. That's expression number 1. So we're going to put a 1 here, right? Again, we've got -2 is less than 1, which is less than 0. So expression, let's just get our order down here. Expression 1 is less than expression, whoa, I just said that totally wrong. You were probably like, huh? Sorry, -2 is less than 0, which is less than 1, of course, which means expression 1 is less than expression 3, which is less than expression 2, right? So our lowest value is 1, then 3, and the expression with the highest value is expression number 2, right? These are just using the expression numbers here. These are what they were actually equivalent to. So our answer for this one would just be 1, 3, 2. So on our Scantron, we would just go ahead and say, starting in the first box, 1, 3, 2. Leave the last one blank because we don't need it. 1, 3, 2. And there we go. All right, so that wraps up that lesson. So you can go ahead and try this one out. This is kind of the recommended one while it's fresh in your brain. But of course, you need more than just one question to practice, so you can work on the rest from the formative assignment. Make sure you're reaching out with any questions or concerns you're having, any that you get stuck on. I'm always happy to help. You can book a meeting or just send an email. But that wraps up the second last lesson of Trig, which is the second last unit. So we are getting unbelievably close to the end here, folks. In the next lesson, we will finish up our Trig unit. Hard to believe. All right.